put in a marker and we'll get going. All right, so spatial partition. Intent. Efficiently locate objects by storing them in a data structure organized by their positions. Motivation. Games let us visit other worlds, but those worlds typically aren't so different from our own. They often share the same basic physics and tangibility of our universe. This is why they can feel real, despite being crafted of mere bits and pixels. One bit of fake reality that we'll focus on here is location. Game worlds have a sense of space. Objects are somewhere in that space. This manifests itself in a bunch of ways. The obvious one is physics. Objects move, collide, and interact. But there are other examples. The audio engine may take into account where sound sources are relative to the player, so that distant sounds are quieter. Online chat may be restricted to nearby players. This means your game engine often needs to answer to the question, what objects are near this location? If it has to answer this enough times each frame, it can start to be a performance bottleneck. Units on the field of battle. Say we're making a real-time strategy game. Opposing armies with hundreds of units will clash together on a field of battle. Warriors need to know which nearby enemy to swing their blades at. The naive way to handle this is by looking at every pair of units and seeing how close they are to each other. Okay, so we have this handle melee unit function, which takes in an array of units and the number of units, which you could probably just get with units.length. So loop through all the units for a plus 1. Okay, so int b equals a plus 1. B is less than number of units. Okay, so look at, this is a basic like standard double loop. We have, we're just going through it, and then for every unit, you're checking every other unit to see if you can handle an attack on them. Here we have a doubly nested loop, where each loop is walking all of the units on the battlefield. That means the number of pairwise tests we have to perform each frame increases with the square of the number of units. Each additional unit we add has to be compared to all of the previous ones. With a large number of units, that can spiral out of control. The inner loop doesn't actually walk all of the units, it only walks the ones the outer loop hasn't already visited. This avoids comparing each pair of units twice, once in eeach order. If we've already handled the collision between A and B, we don't need to check it again for B and A. In big O terms, though, this is still O of n squared. Drawing battle lines. The problem we're running into is that there's no underlying order to the array of units. To find a unit near some location, we have to walk the entire array. Now, imagine we simplify our game a bit. Instead of a 2D battlefield, imagine it's a 1D battle line. Okay, so like we're just basically next to each other on the x-axis. In that case, we could make things easier on ourselves by sorting the array of units by their positions on the battle line. Once we do that, we can use something like a binary search to find nearby units without having to scan the entire array. A binary search has O of log n complexity, which means finding all battling units goes from O of n squared to O of n log n. Something like a pigeonhole sort could get that down to O of n. The lesson is pretty obvious. If we store our objects in a data structure organized by their locations, we can find them much more quickly. This pattern is about applying that idea to spaces that have more than one dimension. The pattern. For a set of objects, each has a position in space. Store them in a spatial data structure that organizes the objects by their positions. This data structure lets you efficiently query for objects at or near a location. When an object's position changes, update the spatial data structure so that it can continue to find the object. When to use it. This is a common pattern for storing both live, moving game objects and also the static art and geometry of the game world. Sophisticated games often have multiple spatial partitions for different kinds of content. The basic requirements for this pattern are that you have a set of objects that each have some kind of position, and that you are doing enough queries to find objects by location that your performance is suffering. So I can see this is like really important for games like the itch.io, like you have the blobs that are eating each other. You don't want to like check if you're eating something that's on a completely other side of the map. That would just slow things down, especially if this is in like an online multiplayer game. You want to check like just who's around you. That's it. Vanawi, hello, hi. Oh, and you have a coding.js flower, awesome. Spatial partitions exist to knock an O of n or O of n squared operation down to something more manageable. The more objects you have, the more valuable that becomes. Conversely, if your n is small enough, it may not be worth the bother. Since this pattern involves organizing objects by their positions, objects that change position are harder to deal with. You'll have to reorganize the data structure to keep track of an object at a new location, and that adds code complexity and spends CPU cycles. Make sure the trade-off is worth it. Imagine Imagine a hash table where the keys of the hashed objects can change spontaneously, and you'll have a good feel for why it's tricky. Yeah, like, that was my first thought, as like a hash table, but yeah, we're constantly changing the keys around. I don't know if that really is helpful then. I would almost imagine that like a tree structure would be right, but at the same time, I don't know exactly how to make it. But good, we're coming up on sample code. So a spatial partition also uses additional memory for its bookkeeping data structures. Like many optimizations, it trades memory for speed. If you're shorter on memory than you are in clock cycles, that may be a losing proposition. Sample code. The nature of patterns is that they vary. Each implementation will be a bit different, and spatial partitions are no exception. Unlike other patterns, though, many of these variations are well documented. Academia likes publishing papers that prove performance gains. Since I only care about the concept behind the pattern, I'm going to show you the simplest spatial partition, a fixed grid. See the last section of this chapter for a list of some of the most common spatial partitions used in games. A sheet of graph paper. Imagine the entire field of battle. Now superimpose a grid of fixed size squares onto it like a sheet of graph paper. Instead of storing our units in a single array, we put them in the cells of this grid. Each cell stores the list of units whose positions are within that cell's boundary. When we handle combat, we only consider units within the same cell. Instead of comparing each unit in the game with every other unit, we've partitioned the battlefield into a bunch of smaller mini battlefields, each with many fewer units. A grid of linked units. Okay, so let's get coding. First, some prep work. Here's our basic unit class. So coding time. So we're gonna have a class. Also, you can go away now. Class units. Friend class grid. Well, we don't do that in JavaScript. So we're gonna have a constructor that takes in a grid, takes in an X, and it takes in a Y. So we're gonna do this dot grid equals grid. This dot X equals X. This dot Y equals Y. We're gonna have a move, which takes in an X and a Y. And it's not gonna return anything. It's not defined here yet. I wonder if this is gonna be a, no, this is not like a virtual class. So it's probably gonna be it is probably going to be defined later in the book for like how we're going to move. Like, are we really moving in the grid, or is this like moving that? Just to test. Oh yeah, no problem whatsoever. It's a pretty fun way to do it. I can remove that here. But yeah, feel free to highlight whenever you want, or if you have a question. Each unit has a position in 2D and a pointer to the grid that it lives on. We make grid a friend class. Okay, so we're gonna have a grid class down here. Because as we'll see, when a unit's position changes, it has to do an intricate dance with the grid to make sure everything is updated correctly. So here's a sketch of the grid. So let's do that next. Class grid. We'll have our constructor. Okay, so we're gonna clear the grid. So we're gonna create a grid. So we have to have cells, and we have to figure out the number of cells. So we're gonna do like this dot cells equals 10 to begin with. This dot cell size equals, we'll just say 20 pixels, whatever that means to us. And then we're going to do this inner loop to create the cells. So we actually need this dot cells equals, so we're gonna have a new array that's the number of cells. So it's gonna be like basically cells down, and then in each row, cells like this. So I suppose it's easiest to create an array like this, right? We just say, all right, we have number of cell, like we just have cells, and then we can loop through the number of cells wide. So for let count equals 0, count is less than this dot cells, count plus equals to 1. All right, so if we do that, then for each cell, we want to create a new array, which is just the number of cells, and that's all we really care about. So we're gonna do this dot cells of position count. So in reality, this should be index. Position index there, and then I want to set this to be a new array, and then we give it the array length, which is this dot cells, and that makes it a square box. This is not valid. It's not going to know which one this is. It's going to overwrite it, so we're going to start with 10, and it's just going to become an empty array, and that's going to cause problems. So this should be cell, like cell count. So then we should do this dot cell count, and you are this dot cell count. But this dot cells, oh nope, got it backwards. You are cell count, and you are cells. There we go. This dot cells of index, because we're starting with a. Oh, you're not gonna be very happy with this. Let's go ahead and make this a new array, and then make this dot cell count as well. This way, we're guaranteed to have a square, and we only have to do a single array for this. No, it wants me to go through everything and like set null for it all. So this, yeah, and unfortunately, I really would love to be able to do this. This is just to create the structure of the array to begin with. Then we want to go through, do this double loop, hit every single cell, and then initialize it to null. So there's a couple ways we can do this. We could just do like the standard loop that we have here. I could map through it, which will create new arrays for each one, but since this is also the initializer, this is not like as bad. Is new array better than just like an empty array? It really depends. In this case, when I do new array, I'm able to pass it in the cell count, so it actually creates an initialized array of this many items, and then I can just loop through that. So here's what this gives me. I can, so before I go cells, because that gives me that specific thing, this allows me to loop through the cells that are going down and then put everything along the side. So that's going to be for index. I can just do this dot cells dot length, because I can already loop through this. Index +1, this dot cells of index, and then create like a new array. So now we have an array of arrays. And now what I want to do is do another double loop through everything. So this is going to be fun. So this is going to be like the index for the y. So we're going to call this y index equals 0. Y index is less than this dot cell count, because we know that it has to be cell count. And then y index plus equals to 1. I like to use very specific names, especially when I'm doing any kind of double like loop with this, because that really sucks. Did I answer your question, Vanaway? I don't want to remove that until I do. Okay, so then our second loop here is going to be for let x index. Also, good morning, Bare Knuckle Waffle. So this is also 0. X index is less than this dot cell count. X index plus equals to 1. I can make this slightly bigger while we're doing this. Yeah, it's I think it's more used in like game development. If I needed the array to be like resizable and like wanted to resize it constantly, then I would probably just create the array and push into it. But this way, I'm guaranteed that I can do something like this and not even use the index. I know what the size is, guaranteed. Okay, so we're looping through, and then we're gonna set the what is it? We're now gonna set the index, like the value for every single point in this grid, to null. So what that means is this dot cells of position y index. Now, the author reverses this down. So the way I'm thinking about it is that outer loop is like along the downside. And that to me is the y-axis. And then the x-axis is along the horizontal. So I actually see this as like opposite. Like the y is like how many down, and then the x is how many across. And I know it looks weird because it's like y first and then x second, which I think that's why it's like traditionally done this way. Just my brain likes to do it, you know, like this. So we set this to null. And constructor takes in that. We've initialized the grid, and there we go. We're done with the grid class. Note that each cell is just a pointer to a unit. Rust hasn't broken you from null, Brooks. Yeah, I know. The problem is that if I did something, like I would have to create something like a class option. And the problem is that there's no, the compiler won't help me. So in reality, I have to think of null as actually none. Like that's what I really have to think of, like in my mind, is that it's none, and I need to like force myself to handle it the way that Rust would force me to handle it. That's sort of like what I'm thinking is going on in my mind, maybe. All right. Note that each cell is just a pointer to a unit. Next will extend unit with next and previous pointers. So class unit, private, unit previous, and next. So this is where it's going to get interesting. So we're going to have a previous and a next inside of here. So this dot previous. And then what are you set to? Like, we don't know what it's set to. Maybe null. This dot next. Just adding more disaster. This lets us organize units into a doubly linked list instead of an array. Each cell in the grid points to the first unit in the list of units within that cell, and each unit has pointers to the units before it and after it in the list. We'll see why soon. Throughout this book, I've avoided using any of the built-in collection types in a C++ standard library. I want to require as little external knowledge as possible to understand the example. And, like a magician's nothing up my sleeve, I want to make it clear exactly what's going on in the code. Details are important, especially with performance-related patterns. But this is my choice for explaining patterns. If you're using them in real code, spare yourself the headache and use the fine collections built into pretty much every programming language today, except JavaScript. Life is too short to code linked lists from scratch. JavaScript has some things, but like not really. However, there are lots of libraries that we can pull in that would do this for us. Yeah, JavaScript is like, it's surprising how bare bones the language is. Okay, entering the field of battle. The first thing we need to do is make sure new units are actually placed into the grid when they are created. We'll make unit handle this in its constructor. Okay, so in unit, we have our constructor here. We've taken the grid, the X, and the Y. So really, this is going to be where it's going into the grid. Now, I have this single suspicion that he's going to treat the X and the Y in the same way that I treated, in the opposite way that I treated the X and the Y here. So I'm going to have to be very careful about this. And like, what are your guys' thoughts on this? I'm really curious, like, do you treat X and Y sort of like this, or do you go the opposite? Because Y is down and the X is the horizontal. Like, to me, that makes sense, but I don't know. I might just have weird brain. Okay, so we have X and Y, our previous and next, and then we're gonna have grid add this. So we need to now call grid. So the cool thing about this is that when I create the unit here, I can pass an instance of the grid in. So we're gonna have an add in here. Let's go ahead and make this smaller again so we can reference the code at the same time. Oh, you were reading something? Oh, does it make sense to you that I have Y and X first before the X? Because the Y is like the down. And like when I think of a grid, I think of like the vertical as the Y-axis and the horizontal as the X-axis. If it was in relation to for looping the matrix, I usually do Y then X on inner row of call. Okay, yes, you do this exact same thing that I do, which is the opposite of what was done here. All right, I'm glad I'm not alone with that. Thank you. Okay, so we're gonna have add here that takes in a unit. The unit knows exactly where it's gonna be, so we can reach into the unit to get this X and Y out. So we're gonna get cell X, cell Y, casting this into an integer, I suppose. Unit X divided by grid size, unit Y divided by grid size. Oh, okay. So the grid, right, because the grid is pixel count. So this is not what grid position it's in. This is like literally, so this might be something like 250 pixels, and this might be something like 300 pixels. Like that's something that it might be. So when we add this in here, we're going to now go into, let's see, const, so cell Y, cell Y equals, convert to an integer, but these are already numbers. Oh, this might be a floating point. This might be like 200.5, 200.4. So if that's the case, we need to floor it. So math.floor. Then inside of here, we're going to grab into the unit. So unit dot Y. I guess in the way that I do this, I can still have like cell X, as long as I'm consistent, right? Then I can grab it from the X position. Then I divide by this dot cell size. Okay, so that gives me like which cell X it's gonna be. And then const, and this is really index X. It's like index X, or as I was putting earlier, X index, Y index equals math.floor unit.y divided by this dot cell size. Okay. Utsby, good morning. I mean, it does have potential performance impacts depending upon your access patterns, but that's not usually a concern you have to think about up front. Right, because we run this and we see whether or not we've got terrible performance. Okay, so that way we get the indexes. Chantilly, good morning. Then we set the previous, so the previous is to null. Add to the front of list for the cell that it's in. Okay, so we're gonna have a linked list in each cell. That's what's gonna happen here. That's really fascinating, and also was really gonna suck when I move into Rust. Because linked lists are not happy, at least normally. Okay, so we're gonna do unit.previous. Make sure that this is set to null, because it's gonna be at the front of the list. Now we already know that it's null, but maybe it was like somewhere else and it's moved around. So that's fine. Then we're gonna do, okay, unit.next equals to the cells at like wherever that. How does that work? This dot cells of position X index, Y index, please. X index. So we're going to put you there. Then cells of, oh, wait a second. That would be the next cell. We're only going to keep one unit in that cell. Okay, I get it. So then we're gonna do this dot cells. A position y index x index is going to be equal to this unit. Now this works in JavaScript because everything that's not like, you know, a primitive value is passed by reference. So this works just fine. And then if the unit next is not null, okay, so then we're going to have to check if our unit dot next. So if that is not equal to null, meaning that there was, like, it was in a previous linked list before, then unit next previous unit. Oh, then basically it's removing itself from that linked list and like adding it in. So it's now saying, okay, unit dot next dot previous. So like whatever the next previous one was, set that equal to the unit. Okay, it's a little bit funny. Okay, so the unit dot next. So basically we have our unit that was like the next thing in the same cell that it was, and it's previous. Like what was that? And then we're setting that previous for the next unit to ourselves. Which, would that put ourselves in like potentially multiple linked lists? Or am I not think like do I need to draw this out to sort of like see what I want it to be? Dividing the cell size converts the world coordinates to cell space, then casting to an int truncates the fractional part so we get the cell index. It's a little finicky, like linked list code always is, but the basic idea is pretty simple. We find the cell that the unit is sitting in and then add it to the front of that list. If there's already a list of units there, we link it in after the new unit. But we haven't like removed it from the previous. Okay, yeah, so we're setting next. Okay, that's what we're doing. We're basically just saying like, hey, if there's other cells in, then we're setting the previous to that one. So it's properly double the linked list. What about the one that it was previous in, like whatever the cell was somewhere else? It's still got a previous to our unit, I think. No, it doesn't. Because we set our unit previous equals null, unit next. I don't know. I still have this like sneaking suspicion that there is like some other linked list that still has a reference to our unit. But I may be wrong, or maybe it's going to be handled somewhere else. A clash of swords. Once all of the units are nestled into their cells, we can let them start hacking at each other. With this new grid, the main method for handling combat looks like this. Okay, so in grid, we're going to handle melee. So that's right here. We're going to loop through all of the cells on, so loop through every single cell, and then call handle cell, and then pass it in that cell. Interesting, okay. And then handle cell is gonna be off of the grid too. All right, so we're gonna have a handle cell, which is gonna take in essentially it's gonna take in a unit. So in here, we're gonna do this like full loop through. So for let y index equals 0, y index is less than this dot cell count, y index plus equals to 1. Okay, then another loop. So for let x index equals 0, x index is less than this dot cell count, x index plus equals to 1. Okay, so now it's going to be this dot handle cell, and then pass in this dot cells of position y index, and of that position x index. Okay, now we know that handle cells is going to come up next. We're going to pass it a unit, but we'll handle that in the next section right here. It walks each cell and then calls handle cell on it. As you can see, we really have partitioned the battlefield into little isolated skirmishes. Each cell then handles its combat like so. Okay, so we now have void grid handle cell. We pass in the unit. While unit is not null. Okay, so while unit, basically while unit, because as long as it's truthy, let's see. While unit is like an object, not null. Unit other. So we're going to create an other equals, okay, so const other equals unit dot next. And then another loop inside of here while other is not null. Okay, so while other exists, if unit x is equal, okay, so if our x positions are the same and our y positions are the same. So basically, like, are we on the exact same, like, x and y, pixels? So this is where we would do, like, the x, this is handle collision. And so in this case, we're looking to see if we're in the exact same x and y position, and that's it. Which is not necessarily, like, if there's like the itch.io where we have like the little blobs that are like eating each other, you have to determine like are they overlapping a little bit. This is where we would like do that kind of collision detection. So in this case, it's if unit.x is if that's equal to other.x and unit.y is equal to other.y. So if that's the case, then handle attack unit and other. And handle attack is probably going to have to be in here too. Which takes in like the first unit, like maybe the, we don't know, like unit A. We'll just do first unit, second unit. We know that there's two units that are attacking each other. Okay, so this is going to be this dot handle attack. We're going to pass in the unit and the other. Now, regardless of what the if is here, we're now going to do other is equal to other dot next. So we're this is still sort of like that loop of loops, because we're just walking through the linked list and just going through, hey, like for every single unit, now check on all the other ones. And then, okay, unit, then check on all those. The other unit, check on all of those. So it's not like the best, but at least we're only doing this for the ones that are in the same sort of square. Now the problem here is that I'm made unit const, so this becomes a let. And then down here at the end of the first while loop, or the inner while loop, before we end this one, we're now going to do unit equals unit dot next. All right. Aside from the pointer shenanigans to deal with walking a linked list, note that this is exactly like our original naive method for handling combat. It compares each pair of units to see that if they're in the same position. The only difference is that we no longer have to compare all of the units in the battle to each other, just the ones close enough to be in the same cell. That's the heart of the optimization. From a simple analysis, it looks like we've actually made the performance worse. We've gone from a doubly nested loop over the units to a triply nested loop over the cells and then the units. The trick here is that the two inner loops are now over a smaller number of units, which is enough to cancel out the cost of the outer loop over the cells. However, that does depend a bit on the granularity of our cells. Making them too small and the outer loop can start to matter. Charging forward. We've solved our performance problem, but we've created a new problem in its stead. Units are now stuck in their cells. If we move a unit past the boundary of the cell that contains it, units in the cell won't see it anymore, but neither will anyone else. Our battlefield is a little too partitioned. To fix that, we'll need to do a little work each time a unit moves. If it crosses a cell's boundary lines, we need to remove it from that cell and add it to the new one. First, we'll give a unit a method for changing its position. Okay, so we have in unit, we're going to have a move. We have that right here. So X and Y, and then this is going to be grid move X and Y. Okay, so this is going to be just calling move down here. So we're going to have a move here also. We're going to take in a unit and an X and a Y. So this is going to be this dot grid dot move, passing this X and Y. Pretty much exactly the same as they have it here. Presumably, this gets called by the AI code for computer-controlled units and by the user input code for the player's units. All it does is hand off control to the grid, which then does this fun thing. Okay, so in here we have the grid. So we're taking in a unit and an X and the Y position. See which cell it was in. So here's where we determine if we're going to move it out of the cell. So we have the old cell X. So we're going to have const old Y index. So this is going to be the unit. So the unit dot Y divided by this dot cell size, and we have to math.floor that. We can't forget that. Const old X index equals math.floor unit dot X divided by this dot cell size. See which cell it's moving to. Okay, so we have our cell X and our cell Y. So this is where it wants to go. Okay, this is the new X and the Y. All right, so const, this is going to be the Y index to remain consistent. Floor, so this is going to be the X divided by this dot cell size. Const X index equals math.floor Y divided by this dot cell size. Okay. So we have those indexes. then we're going to set, now we're going to set the unit to have its new position. So unit.x equals x, unit.y equals y. If it didn't change cells, we're done. Okay, I was wondering about like when we were gonna do that. So this is like where we're gonna move it around the cells if necessary. So if the old cell, okay, so now we're gonna check to see the indexes to see if they're the same. So if old x index is equal to x index and old y index is equal to y index, so if those are the same, then we're just going to return. We're done. Unlink it from the list of its old cell. Okay, this is what I was really concerned about with this like entire handle cell thing. This is where we handle that. So if we reach this point, we are changing cells. We're now going to unlink it from the list of its old cell. So if there is a previous, so if unit.previous, if that exists and is not like, null or undefined or something, then we're going to say unit.previous.next. So reaching in, going back, and then getting the pointer to ourselves, and we're going to set that to the one that we have next to us. So it's going to be unit.next. Which of course, next might be null, and that's fine. And then we're also going to check, so if unit.next, so if we have something that's next in our list, then we're going to do the exact opposite now. So unit.next.previous is going to be equal to unit.previous. And if it's head of the list, just remove it. Okay, so if this dot cells, so a position, the old x, okay, so we basically want to check to see, are we the unit, are we the head, essentially. So, okay, so if this dot cells of the old y index, old x index, if that is equal to unit. Now this works in JavaScript because we're checking to see if the pointer, so like the reference between ourselves and the unit, is the same. Like, are we pointing to the same place in memory? And then we're going to do, so then this dot cells of position old y, old x, set this equal to unit.next. Like let that equal there. And then finally, add it back to the grid at its new cell. And do we have, here's the add unit. So now it's added into the appropriate unit where it's supposed to go. So this dot add and pass it in the unit. Well, that's fun. That's a mouthful of code, but it's pretty straightforward. The first bit checks to see if we've crossed a cell boundary at all. If not, all we need to do is update the unit's position and we're done. If the unit has left its current cell, we remove it from that cell's linked list and then add it back to the grid. Like with adding a new unit, that will insert the unit in the linked list for its new cell. This is why we're using a doubly linked list. We can very quickly add and remove units from lists by setting a few pointers, with lots of units moving around each frame. That can be important. At arm's length. This seems pretty simple, but I have cheated in one way. In the example I've been showing, units only interact when they have the exact same position. That's true for checkers and chess, but less true for more realistic games. Those usually have attack distances to take into account. This pattern still works fine. Instead of just checking for an exact location match, we'll do something more like if the distance of unit and other is less than attack distance. So hold on, where would we do this? Okay, handle attack. Yeah, because like you might be, we have to check like across multiple cells. So is this in handle attack? No, it would be in here. Because we're gonna call handle attack. So distance, unit, and then the other unit. Okay. Is less than the attack distance, then go ahead and do that. When range gets involved, there's a corner case we need to consider. Units in different cells may still be close enough to interact. Yeah, this is the big problem. And this gets especially worse if we're in the corner here, right? Because then we can attack everyone in 4 cells. And not even just everyone in 4 cells, maybe just the people close to the edge of those cells. Here, B is within A's attack radius, even though their center points are in different cells. To handle this, we will need to compare units not only in the same cell, but in neighboring cells too. To do this, first we'll split the inner loop out of handle cell. Okay, so here's this inner loop here. So we're gonna split that out. So let's see. While handle, oh, there's gonna be a handle unit now. I see. Handle unit, which is gonna take in a unit and an other. And so that's where this loop is gonna come in. So I'm gonna just walk this down there. All right, so while other, if the distance between unit and other is less than, okay, so then we're gonna have like some kind of distance method that's maybe like global or something. It's actually pretty, like a lot of vector math, like if we're using some kind of vector, we might be able to, and I don't mean vector as in like the array vector that we see in like Rust or C++. I mean vector is in the mathematical vector, which has the ability to get the magnitude. So if the magnitude of these 2 units is less than the attack distance. So that's fun. Okay, so if we have something like, what is it? It would be, I can't remember in P5, and I think it's something like if unit dot, I don't think it's like magnitude, it might be like distance. So we probably should do something like this. Const distance equals, we'll do something like unit dot magnitude, or maybe like distance. I don't know. We'll have to like do something. Maybe there's some like a utility. So like we could just say like, okay, there's like a utility method, and we can call utility dot distance and pass in unit and other. And so that gives us the distance here. And so now I can call distance if that is less than attack distance, which would be some global that we set somewhere. then we're going to handle attack and pass in the unit and the other. Otherwise, we just continue on like normal. Now we have a function that will take in a single unit and a list of other units and see if there are any hits. Then we'll make handle cell use that. So handle cell. So we figure out, we get the unit from the cells. Oh, interesting. So handle cell is going to take in an X and a Y now. So this is going to be different than this. So we can take an X and a Y. We're going to figure out what the unit is. So const unit equals this dot cells of position Y, Y of position X. Then while unit is not equal to null. Okay, so while this unit actually exists, then we're going to pass handle unit. This one stays the same because we're still going to walk through this this linked list here. But now we're going to do this dot handle unit. We're going to pass in the unit and then the unit next. So unit dot next. Now, unit dot next might be null. I mean, that's a possibility, right? Unit next might be null, and if that's the case, then this won't really work very well. Distance is going to have to handle the fact that, you know, other. So we need to like, if we like drop into like our Rust mindset really quickly, and we say, okay, well, this is going to be like an option unit next. We know that unit exists, but we don't know that unit next exists. What happens? Well, we can't really handle a collision if there's like an other. So we shouldn't even call this if there's not a next. So we should do an if statement. So if unit.next, if that exists, then we can do handle unit, and then we might as well do this, right? There's no point to assign it to even next. No, I do. Well, hold on. I do want to do this. That will result in an infinite loop if I didn't do that. Okay. So that way we always know that other is going to be a thing. There we go. Yep. All right. Curiosity benchmark 100 million iterations. F32 as I64 and F32 is faster than F32.floor in Rust. Really? Is that with the newest compiler? Like with that new change they just made to make it safer to convert F32s to I's, like F's to I's? Wait, you're doing F34 to I64 to F32. Whoa, that, okay, interesting. F64 is I128 as F64 is still slightly faster than F64.floor, but not much. Your stable, okay, so that's the newest thing. Interesting, weird. Still don't know if I want to do that. I don't know if it's worth that. All right. Those additional handle unit calls look for hits between the current unit and units in 4 of the 8 connecting cells. If any unit in those neighboring cells is close enough to the edge to be within the unit's attack radius, we will find the hit. The cell within the unit is U, and the neighboring cells it looks at are X. So let's double check this. Like, are we actually doing that properly? Because handle cell needs to be updated now. Because this needs to just, instead of this dot cells to pass in a unit, this needs to now pass in the y index and then the x index, right? Or is it? Yeah, like this has to make a change. I don't know if they're going to make the change in here or if they forgot. We only look at half of the neighbors for the same reason that the inner loop starts after the current unit, to avoid comparing each pair of units twice. Consider what would happen if we did check all 8 neighboring cells. Let's say we have 2 units in adjacent cells close enough to hit each other, like the previous example. Here's what would happen if we looked at all 8 cells surrounding each unit. Line 4, let's see. X and Y order. Yep, you got it. Thank you. X there and Y there. Vonaway, thank you very much for that help. That is awesome. All right. Let's say we have 2 units in adjacent cells close enough to hit each other, like the previous example. Here's what would happen if we looked at all 8 cells surrounding each unit. When finding hits for A, we look at its neighbor on the right and find B. So we'd register an attack between A and B. Then, when finding hits for B, we would look at its neighbor on the left and find A. So we'd register a second attack between A and B. Only looking at half of the neighboring cells fixes that. Which half we look at doesn't matter at all, as long as we're consistent. There's another corner case we may need to consider too. Here we're assuming the maximum attack distance is smaller than a cell. If we have small cells and large attack distances, we may need to scan a bunch of neighboring cells several rows out, which would suck. So that's something we'd probably want to consider, especially if like we have a design team that's designing like attack distances and the developing team. We might want to like dynamically make the cell size the same as the attack radius. So that way we're never like looking more than one size like of cells out. Utsby, is that sort of type conversion fully equivalent to floor and rust? Oh, you're asking bare knuckle waffle. Design decisions. There's a relatively short list of well-defined spatial partitioning data structures, and one option would be to go through them one at a time here. Instead, I try to organize this by their essential characteristics. My hope is that once you learn about quad trees and binary space partitions and the like, this will help you understand how and why they work and why you might choose one over the other. Is the partition hierarchical or flat? Our grid example partitioned space into a single flat set of cells. In contrast, hierarchical spatial partitions divide the space into just a couple of regions. Then, if one of these regions still contains many objects, it's subdivided. This process continues recursively until every region has fewer than some maximum number of objects in it. They usually split it into 2, 4, or 8, nice round numbers to a programmer. If it's a flat partition, it's simpler. Flat data structures are easier to reason about and simpler to implement. This is a design point I mention in almost every chapter, and for good reason. Whenever you can, take the simpler option, much as software engineering is fighting against complexity. Memory usage is constant. Since adding new objects doesn't require creating new partitions, the memory used by the spatial partition can often be fixed ahead of time. It can be faster to update when objects change their positions. When an object moves, the data structure needs to be updated to find the object in its new location. With a hierarchical spatial partition, this can mean adjusting several layers of the hierarchy. And every time that you adjust anything like that, you're going to add bugs. And I don't even mean like potential add bugs. Like bugs will just get added in. It's, a fact of nature. If it's hierarchical, it handles any empty space more efficiently. Imagine in our earlier example, if one whole side of the battlefield was empty, we'd have a large number of empty cells that we'd still have to allocate memory for and walk each frame. Since hierarchical space partitions don't subdivide sparse regions, a large empty space will remain a single partition. Instead of lots of little partitions to walk, there is a single big one. It handles densely populated areas more efficiently. This is the other side of the coin. If you have a bunch of objects all clumped together, a non-hierarchical partition can be ineffective. You'll end up with one partition that has so many objects in it that you may as well not be partitioning at all. A hierarchical partition will adaptively subdivide that into smaller partitions and get you back to having only a few objects to consider at a time. So I can imagine this as being, let's say we have particles that are like really small, and I'm sort of like randomly creating them and sending them out, but I'm also having them collide with each other and then bounce off. If they end up densely packed into like one section, I obviously don't want them check them colliding up here, or up here when like there's a bunch down here, just collide within each other. But then I see this also if there's nothing, like for some reason, if nothing ends up over here, then I don't want to check them at all. Don't even like just look through that space, only look down here. I could see that being like really important. Does the partitioning depend on the set of objects? In our sample code, the grid spacing was fixed beforehand, and we slotted units into cells. Other partitioning schemes are adaptable. They pick partition boundaries based on the actual set of objects and where they are in the world. The goal is have a balanced partitioning where each region has roughly the same number of objects in order to get the best performance. Consider in our grid example, if all of the units were clustered in one corner of the battlefield, they'd all be in the same cell, and our code for finding attacks would regress right back to the original O of n squared problem that we were trying to solve. If the partitioning is object independent, objects can be added incrementally. Adding an object means finding the right partition and dropping it in, so you can do this one at a time without any performance issues. Objects can be moved quickly. With fixed partitions, moving a unit means removing it from one and adding it to another. If the partition boundaries themselves change based on the set of objects, then moving one can cause a boundary to move, which can in turn cause lots of other objects to need to be moved to different partitions. This is directly analogous to sorted binary search trees like red-black trees or AVL trees. When you add a single item, you may end up needing to resort the tree and shuffle a bunch of nodes around. The partitions can be imbalanced. Of course, the downside of this rigidity is that you have less control over your partitions being evenly distributed. If objects clump together, you get worse performance there while wasting memory in the empty areas. If the partitioning adapts to the set of objects, spatial partitions like BSPs and KD trees split the world recursively so that each half contains about the same number of objects. To do this, you have to count how many objects are in each side when selecting the planes you partition along. Bounding volume hierarchies are another type of spatial partition that optimizes for the specific set of objects in the world. You can ensure the partitions are balanced. This gives not just good performance, but consistent performance. If each partition has the same number of objects, you ensure that all queries in the world will take about the same amount of time. When you need to maintain a stable frame rate, this consistency may be more important than raw performance. It's more efficient to partition an entire set of objects at once. When the set of objects affects where boundaries are, it's best to have all of the objects up front before you partition them. This is why these kinds of partitions are more frequently used for art and static geometry that stays fixed during the game. If the partition is object independent, but hierarchy is object dependent. One spatial partition deserves special mention because it has some of the best characteristics of both fixed partitions and adaptable ones: quad trees. A quad tree partitions 2D space. Its 3D analog is the oct tree, which takes a volume and partitions into 8 cubes. Aside from the extra dimension, it works the same as its flatter sibling. A quad tree starts with the entire space as a single partition. If the number of objects in a space exceeds some threshold, it is sliced into 4 smaller squares. The boundaries of these squares are fixed. They always slice space right in half. Then, for each of the 4 squares, we do the same process again, recursively, until every square has a smaller number of objects in it. Since we only recursively subdivide squares that have a high population, this partitioning adapts to the set of objects, but the partitions don't move. You can see the partitioning in action reading from the left to right here. Okay, so we can see, okay, we have one big one, and here's like all the objects. There's a whole bunch right here. So we subdivide. Okay, and we keep each divide. And it looks like it's dividing until we have at max 2 in each one. Objects can be added incrementally. Adding a new object means finding the right square and adding it. If that bumps the square above the maximum count, it gets subdivided. The other objects in that square get pushed down into the newer, smaller squares. This requires a little work, but it's a fixed amount of effort. The number of objects you have to move will always be less than the maximum object count. Adding a single object can never trigger more than one subdivision. Removing objects is equally simple. You can remove the object from its square, and if the parent's square total count is now below the threshold, you can collapse those subdivisions. Objects can be moved quickly. This, of course, follows from the above. Moving an object is just an add and a remove, and both of those are pretty quick with quad trees. The partitions are balanced. Since any given square will have less than some fixed maximum number of objects, even when objects are clustered together, you don't have single partitions with a huge pile of objects in them. And then we have this last little section, and then I'm gonna have to get ready for stand up. Are objects only stored in the partition? You can treat your spatial partition as the place where the objects in your game live, or you can consider it just as a secondary cache to make lookup faster while also having another collection that directly holds the list of objects. If it is the only place objects are stored, it avoids the memory overhead and complexity of 2 collections. Of course, it's always cheaper to store something once instead of twice. Also, if you have 2 collections, you have to make sure to keep them in sync. Every time an object is created or destroyed, it has to be added or removed from both. If there's another collection for the objects, traversing all objects is faster. If the objects in question are live and have some processing they need to do, you may find yourself frequently needing to visit every object regardless of its location. Imagine if, in our earlier example, most of the cells were empty. Having to walk the full grid of cells to find the non-empty ones can be a waste of time. A second collection that just stores the objects gives you a way to walk all of them directly. You have 2 data structures, one optimized for each use case. And of course, then there's the C also that has like the other grids and the quadries and everything else that we could look into. So this is going to be really interesting because the next state will be going into Rust to try to implement this here. And I'm not really sure, like maybe looking into quad trees, maybe looking into the libraries that are available for quad trees, or maybe trying to implement a quad tree ourselves. Or maybe try to just do this grid first. And figuring out the lifetimes for it with GGZ is going to be really interesting. So anyways, things to look into tomorrow. I'm guessing this is going to be a multi-day effort for us, going in maybe even into the weekend before I can get that like longer stretch to sort of like really grok how we're going to do this in Rust. But that sounds like a tomorrow problem for me, not a now problem. So with that, I'm going to go ahead and close this code up, go to get cracking, and let's go ahead and stage this and read through chapter 20, Spatial Partition. And I will push that up. I have the code is available at repo, bang repo. So you can go take a look at that and add in that. Do you smell oct trees in the future? I have no idea. Grid should be pretty straightforward. Quad tree will be fun. Yeah, this will be very interesting. And I expect that my sort of like concern about this really is just my the preparation for me learning a lot. because I don't know quad trees right now. So I'm looking forward to that. Anyways, with that, I'm going to switch to ending. And thank you everybody for stopping by and watching as I read through this code and convert it to JavaScript. Tomorrow, as I mentioned, is going to end up being a Rust day. So we're going to go through this code and implement it as best we can in Rust and GGEZ, and see if we can get something running, probably with the some particles. And so with that, I hope that you have a great rest of your day, and I shall see you next time. Bye.